Hi, this is the 13.2 video. It is on limits and continuity with functions of multiple variables. So they start talking at the bottom of page 694 about limits. This is the first thing that's in here. And so here, I'll just let you read this on your own at the bottom of page 694 and show you, where is it? This on page 695. It's talking about the delta epsilon definition of a limit, which we don't normally do. It's for definition purposes, not computational purposes. But anyway, we'll just show you a couple of the differences between limits in Cal A, functions of one variable, and limits now in Cal C with functions of 2 or 3 or more variables. So before, if you had looked at the limit with the delta epsilon definition, there would have been this interval on either side of the value that you were approaching, and now there's a disk as opposed to an interval, and so that would be the difference in terms of the definition, because the domain is, because it's a function of 2 variables, the domain is 2-dimensional, and so the domain would be some region in the xy plane. And so instead of approaching a single x value like x approaches a, now you have ordered pairs approaching ordered pairs. And so it's instead of an interval on either side, it's a disk all the way around. And then the other difference would be in terms of the direction of approach. So if you had a picture like this from Cal A, right? If you were going to take the limit as x approaches 1, you could approach from the left or you could approach from the right. And then if you got the same answer from both directions, because there were only 2 directions then you would say that the limit existed, and it's whatever that was. Or if you approach from different directions, you could say, okay, I approach from the left and I get 1. I approach from the right and I get 2. Those are different, so the limit does not exist. So in Cal A, you could use the left-hand limit and the right-hand limit to show that it does exist or that it does not exist. You could do it either way. But now what's different in Cal C with the functions of multiple variables is if you look at it, say, like a sphere. And let's say say this is a unit sphere. So let's say you were going to approach 0, 0, 1, this point. Well, you could approach it from the left, or you could approach it from the right, or you could approach it from the front, or you could approach it from the back, or you could approach it, diagonally this way or this way. So if you think about it, just like a ball and a dot on the top of the ball, there's infinitely many directions that you can approach that point from. And so now, because there's infinitely many different directions that you can come from instead of just the left and the right like before, there's no way that you could check them all and show that they all were the same number. And so as a result of that, you cannot use different paths to show that the limit exists, because what you would have to do would be show that the limit was the same along every single path, but there's infinitely many paths, and there's no way you can check infinitely many paths. So you cannot use the different path approach to show that the limit exists, but you can use the different path approach to show that a limit does not exist if you approach along different paths and you get different limits. Okay, so in terms of notation, this is what it would have looked like in Cal A. The limit as x approaches a of f of x equals L, and so the y values were approaching this y value as the x values were approaching this x value. So now what it's going to look like is, again, because our domain in a function of 2 variables, our domain is 2-dimensional, so we have the ordered pair xy approaching some ordered pair, and here they would be numbers, just like here the a is a number, here these would both be numbers. And then that's going to equal some z value. So here it was equal some y value. Here it's going to be equal to some z value, because f of xy equals z. So f of xy, the function value, approaches some L, the z value, as the ordered pairs xy approach some ordered pairs, and again these would be numbers, x naught, y naught. Okay. All right, so they have, let's get over here, on page 696 in this theorem 1, some of the same rules that you had from Cal A for limits. And so you can look at those on your own. It's, again, the same ones from Cal A, just showing that here they apply to functions of multiple variables. And then Next in this section is continuity. So on page 698, they have the definition of continuity for functions of two variables. This is the same definition as you had in Calais. So it looks a little different in terms of the pieces, but it's the same thing. So the function has to be defined. So instead of it being defined at some x value, it has to be defined at some ordered pair. The limit has to exist, and the limit value, which would be this, and the function value, which would be this, have to be the same thing. So the function has to be defined, the limit has to exist, and they have to be the same thing. So that's the three conditions that have to be met for a function to be continuous. And so they have a little bit more information about that here, right above example 5 on page 698. And then they talk about what I was talking about the limits here on page 699. They're kind of jumping around out of order. This is the different path thing, and so showing that along different paths you get different limits would be how you would show that a function does not exist. So in Calais, to show something did not exist, you normally would graph it and show that the left-hand limit didn't equal the right-hand limit. But here, this is how you're going to show that something does not exist. Okay. And so then here this is, well, it's talking about straight lines, but it could be paths in general. Having the same limit along different paths does not imply that the limit exists. Because again, infinitely many paths, you can't possibly check them all, and so you can't show that they would all be the same. All right, and so I'm not going to read this page to you, but if you look on page 700, there's a lot more information here. Continuity of composite functions, functions of more than two variables, and then extreme value information here. So just read page 700 either now by pausing the video or later when you finish watching. All right, but we're going to look at some examples. So here, these are limits, and these are on page 700. Okay, so first one we're going to look at is number 2. So the first thing always that you should try is plugging it in. I call that plan A. Plan A is what I call it, but it's plug in. So you would take the ordered pair, 0, 4, plug 0 in for x, 4 in for y. As long as you don't get something undefined, like for instance 0 in the denominator, or a negative under a square root, or 0 or a negative in a log, as long as it's nothing like that, then it works when you plug it in and then you're done. So plan A is always what you should try first, plugging it in. All right, so I plug in here, I get 0 in the top, 2 in the bottom. That's okay. I can't have 0 in the bottom, but I can have 0 in the top. So that would just be 0. So then I'm done plugging it in. All right, so same idea here. Plug in pi over 2 for x, plug in 0 for y, see what you get. I get 2 over -1, which is -2. So that is okay, so plugging in works. Okay, so sometimes it's just that easy. Sometimes all you're doing is just plugging in. But now let's look at somewhere it's not that easy. All right, number 14. So I didn't actually show the work where I plugged it in. I did it in my head. But let me just show you here, if you watch for a second. If you plug in the 1, 1, then this would be 1 minus 1, which is 0. 1 minus 1, which is 0. 0 over 0 is not okay. It does not matter what's in the top. If you get 0 in the bottom, that's always a bad thing, regardless of what's in the top. So 0 over 0 is not 1. It's not 0. It's not okay. It's bad. You can't do it. So that would be bad. So you tried plugging in, which was plan A. That didn't work. So now you've got to move on to what I call plan B. And plan B would be algebra. So if plugging in doesn't work, try algebra. Okay, and so algebra again is what I call plan B. Algebra, in this case, it's different algebra depending on the problem, but in this particular problem, the algebra that we're going to use is factor and cancel. So to factor and cancel, the top is the difference of squares. So I factor it as the difference of squares, and then notice I can cancel the x minus y's. What was causing me a problem was having 0 in the denominator. So if I can get rid of the denominator, I've gotten rid of my problem. And so that's why the factoring and canceling is a good approach, because you cancel out the denominator, which was what was causing you your problem. So now that I've canceled, I just have x plus y. Now I switch back to plan A, which would be plugging in. And so I have 1 plus 1, which is 2. Okay, so that was a factoring and canceling example. All right, so next one. Again, I didn't show the work because I did it in my head. But if you plug in the point to -4, you're going to get 0 over 0. 0 over 0, again, is a bad thing. So plugging in did not work. If plugging in doesn't work, switch to plan B, which is algebra. So algebra is, again, here going to be factoring and canceling. This is a different kind of factoring, though. When you have 4 terms, the factoring that you're going to do is factoring by grouping and then pulling out the greatest common factor. So I'm going to group these 2 together and these 2 together and pull out what they have in common. So here you can see they both have xy. Here they both have a 4x. So I pulled out the xy. This is what's left from the first 2 pieces. Then I pulled out a 4x. This is what's left from the second 2 pieces. And then notice this piece and this piece, they both have an x minus y. So I can factor out, not x minus y, x minus 1, I'm sorry. I can pull out the x minus 1 from both pieces. So if I pull out the x minus 1 from here, I'm left with an xy. And if I pull out the x minus 1 from here, I'm left with a 4x. So that would look like this. Factor out the x minus 1, here's what's left. Then this has stuff in common. They both have an x. So I can factor out that x, leaves me with y plus 4, which then will cancel with the top. So this is the factor and cancel algebra approach. And so that canceled out. Oh, it's on the next page, hold on. And so now when I try to plug in, I do not get 0 in the denominator any longer. So I can do the plugging in and I get 1/2. Okay, so that would be the factoring and canceling portion of algebra. Algebra, again, has several different things within it. Like algebra is the broad category, and then there's several different little subcategories in there. So factoring and canceling is the first one. This next one that we're going to look at, again, I didn't show the work for plugging it in, but if you plug in the 2, notice here 2 plus 2 is 4, square root of 4 is 2, so 2 minus 2 is 0. So I get 0 in the denominator, so that's not okay. So plan A does not work. Switch to plan B, which is algebra. Factoring and canceling is not going to work here because this doesn't factor. So it's still plan B, which is algebra, but different kind of algebra. So factoring and canceling doesn't work. If you have a radical, then the method that you're going to use is radical conjugate. So radical conjugate, you would take the part that has the radical and you would use the same pieces, but you would change this sign in the middle. So if the sign was a minus, you use a plus, and if it was a plus, you use a minus. And so notice what I'm multiplying by is equivalent to 1, and so it's legal. But what you want to do on the radical conjugate approach is the part that actually has the radical conjugate pieces, which is the denominator in this case, you do want to multiply it out. But the other part, the top here in this case, don't multiply it out, okay? Don't multiply it out, because just like in factoring and canceling, after you factored, you wanted to cancel. Here, after you do the radical conjugate, you want to cancel. And if you distribute and multiply out that top, you're not going to be able to cancel. So don't multiply out the part that does not have the radical conjugate pieces. Okay, so the way the radical conjugate works, I didn't show the work on here, but when you're doing FOIL, the F piece, this times this, notice that the square roots will cancel and just leave you with x plus y. But then on the O and the I piece of FOIL, you have this square root times positive 2, and then you have the square root times negative 2, so those are going to cancel. So in radical conjugate, always the O and I piece of the FOIL, they'll cancel out because they'll be the same thing but with different signs. And then you have the negative 2 times 2, which is negative 4. So you end up with this in the denominator, x plus y from the F piece of FOIL minus 4 from the L piece of FOIL. And so, again, don't multiply out the top, because see how now it's going to cancel? If you would have multiplied it out, that wasn't going to work. So now you can cancel this and this, and so it's just going to leave you with this. And now you can plug in, and so you end up with 4. Okay, so that's, again, algebra, but it's the radical conjugate part of algebra. Okay, now let's look at functions of more than 2 variables. So 28 is a function of 3 variables, because notice I have an ordered triple. So this is x, this is y, this is z. Always try plan A first, which is plugging in. And here, when I plug in, notice the 2's cancel, so this is negative pi over 4. Notice this is tangent inverse. If it was tangent of negative pi over 4, then that would just be negative 1. But this is tangent inverse, so you can't do that without a calculator. So you just leave it like that since we can't use calculators. All right, I'm going to go a little bit out of order now because the next group of problems is on continuity, and I want to finish talking about limits while we're here. So I'm going to skip this stuff in the 30s and move on to this 41 to 48. So 41 to 48, you have, they're kind of ruining the surprise for you. It says by considering different paths of approach, show that the functions have no limit. So in other words, you're trying to show it does not exist. But let's pretend like you didn't already know that, and I'll show you how you could tell that that's what you're supposed to do anyway. So if you look at this problem, okay, the first thing you should try is, oh, whoops, I guess it would help if I looked at the limit. Hold on. Let me write it down. Sorry, I can't hold the phone and see what I'm doing when I'm writing. Okay, so it told you in the directions that we're approaching 0, 0. All right, so this is what it would look like. So let's look at this. Sorry, that's super messy. So plan A, try plugging it in. Okay, you get 0 in the denominator. That doesn't work. Switch to plan B, which is algebra. Okay, you can't factor and cancel because this is the sum of squares, and it doesn't factor. They have nothing in common, so you can't do Gray's common factor factoring. So it's not going to factor. You can't do radical conjugate because there's no radicals. And so algebra doesn't work. And so if you try plugging in and it doesn't work, you switch to algebra. If you try algebra and it doesn't work, that was plan B. If plan B doesn't work, you try what I call plan C, and that is the different paths. Okay, so here's the plans. So plan A, these are what I call it on the left. This is what it actually is on the right. Plan A, plug it in. If that doesn't work, plan B, algebra. If that doesn't work, switch to plan C and use different paths to show that the limit does not exist. So plan C is the different path approach. So this one is going to be the different path approach. You can use any path you want to. There's infinitely many paths. If you look at the book, they use some crazy, ridiculous paths, and you think, where in the world did they get this from? And the answer is, I have no idea. So you can choose whatever you want to. So you can choose crazy, ridiculous ones if you want to, but these are the 3 that I recommend. The 3 that I recommend is x equals 0, y equals 0, and y equals x. So that would be along the y-axis, x-axis, and this slanted line. Those are the 3 that I recommend you try first, because usually, and not always, but usually that's enough to show that it doesn't exist. Okay, so those are the 3 that I recommend: x equals 0, y equals 0, y equals x. So let's look at some. 42, same problem. So we're going to first try the path y equals 0, which is the x-axis. All right, so this is the problem, and I'm doing it along the path y equals 0. So if it's y equals 0, all of my y's are going to become 0, and I'm just going to be left with x's. So because my y becomes 0, see how it's just x's left? So it's just going to be x is left. X is approaching 0. So I have x to the 4th over x to the 4th, which simplifies down to 1. And then when I take the limit of 1, that's 1. Okay, so that's the limit along this particular path. Now I'm going to try the path x equals 0, which is along the y-axis. So same idea, but now because I'm going along x equals 0, all of my x's are going to become 0, and all that I'm left with is going to be y's. So x's become 0, I'm just left with y's, and then I have, that would be 0 over y squared, which is 0, and so the limit of 0 is 0, because 0 over y squared is 0. So notice what happened. Along this path I got 1, along this path I got 0. Those are not the same thing. And so if I get different things, the answer would be that the limit does not exist. Okay, so the limit does not exist. All right, let's look at one where you have to try more than 2 paths. So this is 48. 48, here is my function. Okay, so I'm going to try the path y equals 0. So if y is 0, all of my y's are going to become 0s. So I have 0 for the y's. That's 0 over x to the 4th, which is 0. Limit of 0 is 0. And then here, I'm going to try x equals 0. So all of my x's are going to become 0s. All that's left with is y's. I have 0 over y squared, which is 0. Limit of 0 is 0. I got the same thing. Do not say, hey, I got the same thing, so the limit must be 0. No, you tried 2 paths out of infinitely many. So you have infinitely many more left to try. So just because you got 0 does not mean the limit is 0. Just keep trying. So I'm going to try my 3rd recommended path, the path y equals x. So along the path y equals x, that doesn't look like an x. Along the path y equals x, you can either change all of your y's to x's or all of your x's to y's. I like to change all of my y's to x's because I like x's better. So I change all of my y's to x's. So that y became an x, that y became an x. All that's left is x's. So I have x cubed over x to the fourth plus x squared. I can't plug in because it's going to give me 0 over 0, which is not okay. So try some algebra. Factor this out. Cancel gives me to here, so it's factoring and canceling. Now when I plug in, I get 0 over 1, which is 0. So I'm still getting 0. See, 0, 0, 0. Again, do not say, well, because I keep getting 0, the limit must be 0, because now you've only tried 3 out of infinitely many. You still have infinitely many more to go. It's kind of like eternity. It just never, never ends. It's forever. So infinitely many paths, you can never, ever try them all. Okay. All right, so you're trying to keep trying. You're going to keep trying. That sounds weird. Anyway, I can't talk today. My daughter made me go to Sub-Zero yesterday to eat ice cream that they make with nitrogen, and it literally burned my tongue, like cold burned my tongue. And so my tongue still hurts, so I can't even talk so don't eat ice cream made out of nitrogen. It's very painful. Of course, I think it's just me because it didn't hurt my daughter's tongue, but it hurts my tongue because that stupid Sub-Zero ice cream. Never again, never again. Anyway, so now I'm going to try a different path. This is not one of the ones on my list because I tried all 3 on my list and they didn't work, so I've got to try something else. But again, normally those 3 will work, but here it didn't, so try something else. Now I'm going to try x squared. So I'm going to, excuse me, replace all of my y's with x squareds. So both of these y's, replace them with x squared. Notice this y was being squared, so it's x squared squared, which becomes x to the 4th. So add those, it's 2x to the 4th. Then cancel my x to the 4th, so it's 1/2. Limit of 1/2 is 1/2. So finally, this is 1/2. The other ones were 0. 0 is not the same thing as 1/2, so the limit does not exist. Okay. All right, so that's what I call Plan C. That's what you would do if the limit doesn't exist. You're going to show it by doing it along different paths. Okay, so now let's go back to continuity. Sorry, I got to rearrange on this. Okay, the directions. This is 31 to 34. It says, at what points in the plane are the functions continuous? So we're going to look at 32. Notice it has 2 parts, A and B. So for part A, I'm looking at this. So basically, I need to make sure that the function exists, that the limit exists, and that they're the same thing. So I'm kind of just looking out for holes, asymptotes, breaks, things like that. So they don't usually have breaks unless they're piecewise functions. They have asymptotes where the denominator is 0, and they have holes where the denominator is 0, but it would have canceled. So basically, you're, in this case, just looking for what makes the denominator 0. So it's continuous as long as the denominator is not 0. So if you move this y over, it's continuous as long as x does not equal y. So it would be continuous for all ordered pairs, because remember the domain is 2-dimensional, it's ordered pairs. Continuous for all ordered pairs such that the x and y coordinates are not the same. Okay. All right, so let's try part B. Part B, same problem. I don't want a 0 in the denominator. However, because x squared is always 0 or positive, when I add 1 to it, it's always 1 or bigger. So it's never going to equal 0, which means the denominator will never have a 0 in it, which means it's always continuous. So again, do not say all real numbers. It would either be continuous for all ordered pairs or R2, okay, but not for all real numbers. That's 1-dimensional, and this needs to be 2-dimensional. All right, so let's look at the next group. This is 35 to 40, and this is same thing, but functions of 3 variables. All right, so in 36a, I have a log. Now, logs are similar to denominators in that they can't be 0. They're also similar to square roots in that they have to be positive, so I need this to be greater than or equal to 0. Okay, so it's continuous as long as this is greater than or equal to 0. So notice what this is saying. The product of these 3 things needs to be positive. It's not saying individually those need to be positive because, like, for instance, x could be negative and y could be negative because then negative times negative makes a positive. So as long as z then would be positive, it'd be positive. So it's not that they have to be positive individually. It's that the product of the 3 of them has to be positive. And notice now, because it's a function of 3 variables, it's ordered triples. So continuous for all ordered triples, x, y, z, such that the product is 0. I mean greater than 0. All right, and then lastly, this one, part B, here you can put anything you want to in the power of an e. You can put anything you want to in a cosine. So this one is always continuous. Again, don't say for all real numbers. It would be for all ordered triples or for R3. Okay, so that's continuity, very similar to what we were doing in domain. So it's just like the domain problems from before. All right, that's all from 13.2. If you have any questions, just send me an email.